Today we have another theorem. If f is a function from a to b, and e and f are subsets of a, then the image under f of e union f is the image of e union with the image of f. Part B states that the image of e intersect f is contained in the image of e intersect the image of f. And part C of our theorem says that the image of e set minus the image of f is contained in the image of e set minus f, okay? So first, before we delve into this theorem, let's briefly recall some definitions that we're going to need. So first of all, f of a set E. So this is not just a single point, it's a set. So if E is a subset of, let's say, A, then f of the set E is just the set of all B in our target space, capital B. Remember, B is the target space or the codomain. So it's the set of all B within B such that B is equal to f of E for some E in my set E, okay? This is the definition. Basically, it's all the points in B which are the image of some point of the set E. So if we drew a picture here, here's A, here's B, and then if I have a subset of A, let's say E, then wherever this subset, A is a mapping from the set F is a mapping from the set A to the set B, and F induces a mapping from the subset E into some subset of B over here, where basically whatever points in E, wherever these points get mapped into B, that's me, my set F of E. So it's the image of the set E under the mapping F, okay? And it's a set. Okay, so that's the first definition we need. And then the next definition that we're going to need is this set minus. So, but I'll define the set minus when we get to part C, okay? All right, so before I prove the theorem, let me just explain why B and C are not equalities, okay? So if you saw my previous video, we had, for the inverse function as a set theoretic map, we had equalities in these two parts. But now, if we just look at the image sets, we only have these inequalities. And the reason is the following. So consider, first of all, part B of this theorem, okay? So I'm going to choose a function f which is not one-to-one, okay? So in particular, I want the function f to send two different values, let's say a1 and a2, to the same value b, okay? So f of a1 is equal to f of a2 is equal to b. Then, if I define my set E to be a1 and a2, and then if I define my set F to just be, let's say, a2, okay, then you'll see that that this is actually for part C. So for part C, we'll see that F is a subset of E, right? F is contained in E clearly because F is just the singleton A2, and E contains that singleton A2. So in this case, F is contained in E, all right? And we observe that E set minus F, okay? E set minus F, I just remove the point A2 from E. This is the set A1, okay? So F of E set minus F is just F of A1 as a set. So this is just the set containing the point B, all right? So F of E minus F in this case is the singleton set B. However, F of E and F of F are both also the singleton sets B. So F of E is the singleton set B, and F of F is the singleton set B. And so when I subtract these two sets, I get the empty set, right? I'm subtracting B from B, so this becomes the empty set. So f of e set minus f of f is just the empty set. And so we can see that actually there isn't an equality here. This set is truly strictly contained in this set, in this example, okay? Now for the example for part B, it's even simpler. So for part B, we're going to use the same mapping f. And now look at that. Okay, but this time I'm going to choose E to be the singleton set A1, and I'm going to choose F to be the singleton set A2. Okay, and then here we have that f of E intersect F is the empty set. So E intersect F, these are disjoint sets, so their intersection is empty, and so the image is the empty set, is also empty. However, f of E, so f of E is, again, F maps the point A1 to B, so f of E is the singleton set B, and f of F is the singleton set B. So we can see that if I intersect these two sets, well, they're the same set, so if I intersect them, I just get B. So f of E intersect f of F is the set B. And so again, we can see that this set is, in this specific example, this is the empty set here, and this on the right-hand side is the singleton set B. And so there is a strict inclusion. So equality does not hold in general in these two cases. However, if we were to impose a restriction on F, where F becomes injective, okay, then I believe that these equality, then we would have equality here, okay? All right, so let's go ahead and prove part A. Okay, so again, these are sets, so to prove they're equal, I need to prove both directions of the set theoretic inclusion. Okay, so for this direction, I'm going to let x be within f of E union F. So this tells me that x is in this set. Therefore, there exists, and let's say a letter A within E union F such that f of A is equal to x, okay? By definition of this image set here, okay? All right. Yeah, I should probably state the definition just so you have it. Remember, this is defined to be the set of B within B such that f of A equals B for some A in E union F. Okay? So it's the set of image points of the set E union F. So therefore, any point in this set must be the image of some point A in E union F. So that's exactly what I'm saying here. I'm saying that there's an A in E union F such that the image of A is X. Okay? So this is just unpacking the definition of F of E union F. Okay? So now, if A is in E union F, this tells me that A is in E or A is in F. Okay? And in the case that A is in E, and we still have the property that f of A is equal to x no matter what. We know that f of A is equal to x. So in this case here, we have that that x is in f of E, or in the case that A belongs to F, we know that x belongs to f of capital F. Okay. So again, using the definitions in reverse now. Okay, well this means by definition that x is in f of E union f of F. Okay, so this shows the first direction of the set containment. I've shown that an arbitrary element of this set must belong to this set. Therefore, this set contains the set on the left. Let's prove the other direction. So I'm going to let x belong to f of e union f of f. Okay? Therefore, x belongs to f of e, or x belongs to f of f. Okay? So, in the first case, I have by definition that, that there exists an A in E such that f of A is equal to x, okay? Or there exists an A within f such that f of A is equal to x, and that unpacks the definition of x belonging to the image of the set capital F, okay? All right, so these are just the definitions, unpacking. Wonderful. And so now, in either case, we know that, so one of these statements is true, but we know that A belongs to E or A belongs to F, okay? So this tells me that for certain there exists an A in E or F such that f of A is equal to x. Okay, but now we're pretty much done, because this tells me by definition that x must belong to the image of E union F. Okay, so that proves this direction of the set theoretic inequality. We started with an element in this set, proven that that element must belong to this set. Therefore, this set contains the set on the right. Since we've proven that both sets contain each other, they must be equal. So that proves part A of the theorem. Let's move on to part B. Part B states that f of E union F is contained in f of E union of F. And this should not be a union, this should be an intersection. I apologize. Okay. So, we've already seen that equality does not hold. To prove this direction of the set theoretic inequality, I simply need to let x belong to the set on the left, and I want to show that it belongs to the set on the right, okay? So if x belongs to this set, this tells me that there exists an A within E intersect F such that f of A is equal to x, okay? So therefore, there exists an A in E such that f of A is equal to x, and there exists an A within F such that f of A is equal to x. Okay, so notice that here, this is kind of a weaker statement because I've broken up this. So A is the same element here, and A belongs to E and F. Now here I've just said, well, I know for certain that there's an element of E where the image of this element A is x, and I know that there's another element A in F such that the image of A is x. So this is actually a weaker statement than previous, but certainly this direction is true, right? Because A belonging to this intersection means A belongs to E and A belongs to F. So we are guaranteed that certainly these two statements will hold, okay? But if these two statements will hold, this tells me that x itself belongs to f of E. This is the first statement. And x belongs to f of f, which is the second statement by definition. So therefore, x belongs to f of e intersect f of f. Okay, great. And we can see that in the weakening here, the reason why this is not an equality, logically speaking, is actually to progress from this step to the next, from this line to the next, we actually weakened the statement, right? Think about it, as I explained earlier, this is actually a slightly weaker statement because these a's need not be the same a in this line, but in the previous line, it's just a single a, okay? All right, so that proves B. Move on to C. So C tells us that f of e set minus f should be contained in f of e set minus f. F, is this correct? Let me just think about it. No, it should be the other way, right? F of e set minus f of f is contained in f of e set minus f if f is a subset of f, right? So let me just make sure this is correct. Going back to our example, we had 2 points in A, which get mapped to the same point of B. And so we said that if E was the set A1, A2, F was the set A2, and they both A1 and A2 get mapped to B by F, then we know that F of E set minus F, well, this is just F of the singleton A1, where I've subtracted E from F. This would be a good time to define E set minus F, which is by definition the set of all A within E such that A is not in F, okay? So basically, we take the set E and we cut out the set F, and it's all the points in E which are not in F, okay? And so yeah, so in this case, F of E set minus F is F of A1, because I'm just removing F from E, so that leaves me with just A1. And F of A1 is just the singleton set B, because F maps A1 to B. However, F of E minus F of F is the singleton set B set minus the singleton set B, which is the empty set. And so we see that this is a strict set theoretic inclusion, which tells me that, yeah, this is the correct direction of the theorem, and the other direction does not hold in general. Okay, so let's prove it. Okay, so let x belong to f of e set minus f of f. So then by definition, we have that x belongs to f of e and x does not belong to f of f. Okay, so what does this mean? This means that there exists, the first part of the statement means that there exists, let's say, an A in E with f of A equal to x. And then since x does not belong to f of f, okay, so let's just unpack this. X does not belong to f of f, okay, so what does this mean? Well, we know that if x belongs to f of f, then we must have the existence of some a prime, let's say, I'm just using a different variable rather than a, so existence of an a prime within f such that f of a prime equals x. And so this is a logically true statement. This is the definition, okay? So I take the contrapositive of this statement. Contrapositive, if I have P implies Q, the contrapositive is not Q implies not P. So let's negate this. So the logical negation of this statement is for all A within F. Okay, when I take the negation of the existence sign, it turns it into a for all. Okay, so for all A prime in F, F of A prime, and then I negate this statement, so not equal to X. Okay, so this is the logical negation of the statement on the right, and then by the contrapositive, so this is not Q, implies not P, so X is not within of F. Okay, and actually, right, this is actually a definition. Okay, so X belongs to this set definitionally if and only if there exists an A prime in F such that the image of A prime is equal to X. And so therefore, the contrapositive actually becomes an if and only if. Okay, so we can do the contrapositive in the other direction and conclude that X is not within F of F if and only if for all A prime in F, F of A prime is not equal to X. So therefore, since this specific A within E satisfies that F of A is equal to X, we must have that since X does not belong to F of F, we must have that F of A cannot equal, F of A, so we know that F of A equals X. So this statement is false. Therefore, A cannot belong to F, okay? Because if A belonged to F, then we would necessarily have that F of A is not equal to X. But we know that F of A is equal to X. So since we know that F of A is equal to X, this statement cannot hold, right? Okay, so this is the most nuanced part of the proof, so let me just emphasize this in more detail, okay? So I'm going to keep this statement on the board. So we know that two things. One, we know that this specific A satisfies that F of A is equal to X. And two, we know that X, we know from here that X does not belong to F of F. Now, X not belonging to F of F implies this statement here, okay? That for all A in F, A prime in F, F of A prime is not equal to X, okay? So since F of A is equal to X, okay, then this tells me that A cannot belong to F, okay? Because if A belongs to F, then I must have, by claim 2, I must have that F of A is not equal to X. But I know that F of A is equal to X. Therefore, A cannot belong to F. If that does not make sense to you, please let me know in the comments, okay? All right. So, we're here. We know, so A belongs to E and A does not belong to F if F of A is equal to X. This tells me that A belongs to E set minus F and with the property that F of A is equal to X. Okay, but this by definition tells me that X belongs to F of E set minus F. And that proves this direction because we've taken an arbitrary element of this set and shown that it must belong to the set on the right. Proves that this set contains the set on the left. Okay? All right, there you go.